Swayam Prabha. Digital India. Educated India.
Welcome to the third lecture of the module Design of Worm and Worm Gear. So, in the previous classes of this module, in lecture 1 and lecture 2, we studied about the introductory part of worm and worm gear, its nomenclature, terminologies which are used in this drive, and the force analysis considering the friction and without friction. Now, we will briefly study the nut and bolt analogy and the worm and worm gear drive, and thereafter we will start design of worm and worm gear. So, let us start this lecture. The forces which we determined is between worm and worm gear is given by this, and we may apply the analogy of nut and bolt to get the direction of motion of gear if a particular direction of rotation is given to the worm drive. Now, as we have studied that this worm is just like a screwed member in which along a cylinder a screw is wrapped, or it travels along the length of the worm making an helix angle. So, if this worm is considered as this bolt with a head and the gear is considered as a nut, because this gear is meshed with the worm similar to the nut which is screwed to the bolt. Now, if a right hand thread is there in the bolt and right hand thread is there in the worm, then if we give clockwise motion to the head of the bolt, then this nut advances towards the head of the bolt in the right hand configuration and opposite in the left hand. That if a head is given clockwise motion, then if the thread is left hand, then this nut will move in the opposite direction as shown by this red arrow. So, if the thread on the worm is right hand and rotary motion to the worm is given in the clockwise direction, then the meshed element or the screwed element will move towards this way in the positive z direction. This is the positive z direction. Okay. It means this gear will direct towards this red arrow. This is the red arrow directing towards positive z. So, the directions should be in the similar way for the case of gear also. It should be directed towards this red arrow. Now, if it is directing towards this one, it means the rotary motion to the gear will be in the clockwise direction, okay, like this. Then only this type of directional motion will be. Now, the worm gear forces which we determined is like this way, just repeating it. Now, the relation between sliding velocities. Now, as we studied that in the case of worm and worm gear drive, the motion between the two gears, the worm and worm gear, is sliding motion. Now, the sliding motion means there will be a sliding velocity. So many experiments have shown that the coefficient of friction is dependent on the relative or sliding velocity. Now the sliding velocity will act along the direction of the screw or the tangent to the screw. Okay, tangent to the screw or tangent to the thread of the worm. So in this figure, the worm is shown above the gear. This is the worm gear. The colored is the worm gear, and axis of the worm gear is this one. This is the axis of rotation of the worm gear, and worm is above the gear, and axis of rotation of worm is this one, shown by the green color. This is the axis of rotation of the worm. Okay, and worm is above the gear. That may be shown by a green color like this. Okay, and the thread on the worm is given by this. This is the direction of the thread, and the angle between tangent to the thread and a line perpendicular to the axis of rotation of the worm is called the lead angle, as we had studied in our previous classes. So this is the lead angle. Okay, so the pitch line velocity of the gear, pitch line velocity of the gear is given by this Vg, and the pitch line velocity of the worm is given by this one, Vw, and the sliding velocity is along the thread of the worm, and the angle between Vw and Vs is lambda. So in this figure, Vg is the pitch line velocity of the gear and Vw is the pitch line velocity of the worm, and vectorically these velocities can be represented by this equation. Vw, this Vw is equal to Vg vector plus Vs vector. Okay, Vg vector and Vs vector, and this Vs and cos of the lambda will equal to Vw from this triangle, right angle triangle. Vs is equal, no, Vs cos of the lambda is equal to Vw. So from that we get the sliding velocity in terms of pitch line velocity of the worm. Okay, and that is Vs is equal to Vw divided by cos of the lambda, and Vw we can simply find knowing the pitch diameter of the worm, the rotational speed means RPM of the worm. We can find the value of Vw, and thus we can find the Vs, the sliding velocity. Now the coefficient of friction can be obtained from this figure knowing the sliding velocity Vs in meter per second. The representative values of coefficient of friction for worm gearing is shown here. These values are based on good lubrication. Use curve B, this one, curve B, for high quality materials such as a case hardened steel worm mating with a phosphor bronze gear. Use curve A, this curve A, when more friction is expected, as with the cast iron worm mating with the cast iron worm gear. So it is obvious that for a particular pitch line sliding velocity, if the mating material are high quality materials, then the friction will be lesser. Coefficient of friction is having a smaller value in comparison to the more friction giving materials. For that, the coefficient of friction is something this, which is more than this one. Now, we have one example. A double start right hand worm transmits 0.7 kilowatt power. So, the H is 0.75 kilowatt at 20 revolution per second. So, RPS is of the worm, means small n of the worm is 20, and this is in not RPM but RPS, revolution per second, to a 30 tooth worm gear. Number of teeth in the gear, that means ZG is 30, and number of teeth on the worm will equal to the number of starts of the thread, and double start thread is there, and so ZW is 2, and the threads on the worm is right hand. So it is right hand. Okay. The gear has a transverse module of 4 mm. MT is 4 mm. A face width of 25 mm. Face width F or B, whatever notation is adopted, 25 mm. The worm has a pitch diameter of 50 mm. DW is 50 mm and a face width of 60 mm. Face width of gear F gear or B gear is given by 60 mm. The normal pressure angle is 14.5. Phi n is 14.5 degree. The material and quality of the gearing to be used are such that curve B of figure is used. This is on the slide number 17. Should be used to obtain coefficient of friction. So, curve B should be used. This curve B, quality is good. So, knowing the sliding velocity, we will get the value of F. Now, find the axial pitch, center distance, lead and the lead angle. So, all these you can find knowing the these things. So, the axial pitch is given by pi multiplied by transverse module. Transverse module is 4. Transverse module is 4, and so Px is given by this one. Similarly, you can find other things, and the center distance C will be dW plus dg divided by 2, and that is given by this one, and so it comes as 85 mm. The lead is L is equal to Px multiplied by number of start or thread on the worm, and so it is Px just we have obtained is 12.566. It will be multiplied by 2. So, lead is this one. So, lead angle will be tan inverse of L divided by pi dW, like that. The main thing is determination of the forces on the bearing and the forces on the point of contact. Well, so it is required to determine the bearing reactions. So, one bearing is A, somewhere here. This is the bearing A, and the bearing B is at this location. So, this distance between the bearings is 60 plus 35. Okay. So, if the shaft is represented by this along the x axis, this is the x direction. and the vertical direction is the y direction. This is your y and this is z. Okay. So this is your A point. Somewhere here is the B point, and at a distance of 35 along the x-axis, at a distance of 35, this distance is 35, at a distance of 35, and at an height of d gear divided by 2, because the point of contact where the forces will be transmitted from worm to the gear is lying along the y direction, and that will be at a distance of half of the pitch diameter of the gear. So from this point, if we move along the y direction at a distance of this distance equal to dg divided by 2. So this will be the pitch point P where all forces will act. Okay. So the transmitted load will act in the direction of rotation of the gear, because it is a driven gear, and for this case the transmitted load will act opposite to its rotation, and the rotation given is like this. It is rotating in this way. Okay. It is rotating in this way. It means along the positive x direction is the direction of rotation at the point of contact, and in the opposite direction the transmitted load will act. So WWT will act along the x-axis but opposite to the direction of positive x. So it will act in the negative x direction. So in the negative x direction, the force will act on the worm. So on the gear, it will act in the direction of positive x, and that will become the axial force for the case of gear. Okay. So for the case of gear, because this axis is the axis for the gear, so the forces will be taken which will be acting on the gear. So along the x direction will be the axial force, and it will act in a positive x direction. Okay. It is WGT, positive x direction. Now the radial force is obvious, will be acting along the axis of rotation, and so along the y direction but in the negative y direction. So your WG radial will be in this way. Okay. Now the one thing I have written wrong here, this is the axial force. Axial we have found, because on the gear it will be the axial force, and the axial force will be the transmitted force for the worm. Okay. So let me change the, this is WGA, and WGA will equal to minus WW transmitted. Okay. Now the other force which is remaining is the transmitted force for the case of gear, and the transmitted force will act in the direction of its rotation, and direction of its rotation will be the WG tangential. It will act along direction of rotation, and this will also equal to W axial, isn't it? So let's find the this thread is a right hand thread, and so when you will give it a clockwise rotation, like that, this type of clockwise rotation from this side, then this gear should come in this direction. Okay. Now here the motion is given in anti-clockwise direction, and so it should not come here, but it should go away from this. And when it is going away from this, the meaning is its rotation will be just like this, shown by this arrow, isn't it? So direction of rotation of the gear is this one, and so in a similar direction will be the tangential load or the transmitted load, Wg transmitted. So Wg transmitted is acting along z axis but opposite to the direction of z. So this will be the direction of Wgt. Now your next step will be to determine the values of this Wga, Wgr and Wgt from the formulas which we have studied, and thereafter get the reactionary forces at B and A. Reactionary forces will be Rb in the direction of y, Rb z in the direction of z, and one of the bearing either at A or B will act like a thrust bearing. So is it given in your problem? Let's see. Figure given below is a drawing of the worm gear oriented with respect to the coordinate system described earlier in this section. The gear is supported by bearing A and B. Find the force exerted by the bearings against the worm and gear and the output torque. So in this problem, it is not specified which bearing should take the thrust load. So you can select any one, either A or B. So let bearing A is to support the thrust load, and so the reaction will be there at A, and reaction we will take in the direction opposite to the direction in which the axial load is acting at the pitch point P. It is acting in the positive x direction, so the reaction will be taken R A x in this way. This is R A y, and in the z direction will be R A z. Okay. So we have 1, 2, 3, 4, 5 unknowns, in addition a torque on it. So by applying the static equilibrium equations, you can find these forces very easily. This is shown here, the forces which are here acting on it. This distance is dg divided by 2, that is 60, and this P is 60 mm. The forces at bearing B, forces at bearing A. Okay. In here the bearing B is taken to support the thrust load, so the bearing reaction along the x direction is taken here. So anything you can do if it is not given. Now the next thing which we are going to study is we studied this part of this module, this part and this part. Now the worm gears bending stress analysis we are going to study. Cylindrical worm dimensions common to both worm and worm gear is given here. and this we studied in our previous class also. In addition is the table 4.2, the minimum number of teeth in the worm gear. What should be the minimum number of teeth to avoid interference? With the pressure angle, different pressure angles, the number of teeth on the gear minimum is given. So, if 14.5 is there, so the minimum number of teeth on the worm gear should be 40. With the increase in pressure angle, the minimum number of teeth on the gear is reduced. Then the maximum lead angle for normal pressure angle. So, with the pressure angle of 14.5, 20, 25 and 30, the maximum lead angle that can be taken is 16, 25, 35 and 45. Now, worm gear bending stress analysis, because worm teeth are inherently much stronger than worm gear teeth, they are not considered for this analysis. The teeth in worm gears are short and thick on the edges of the face. Mid plane they are thinner as well as curved because of the enveloping nature. The teeth is something like this due to enveloping. Okay. So, it is said that the worm gears are short and thick on the edges, but mid plane, at the mid plane they are thinner as well as curved. AGMA relates the tangential force on the worm gear tooth WGT to other parameters by WGT is equal to CS multiplied by CM multiplied by CV dm to the power 0.8 multiplied by FEG. Let us see what the terms are, where CS is the material factor, dm is the mean pitch diameter of the gear, mean diameter or the pitch diameter you may take of the gear. Fe is the effective face width of the gear, actual face width but not to exceed 0.67 dm, the mean worm diameter in mm, and Cm is the ratio correction factor and Cv is the velocity factor. The friction force Wf is given by the formula which we had derived. Wf is equal to Fw normal, and that is Fwgt, the tangential force on the gear, divided by coefficient of friction multiplied by sine of the lead angle minus cos the normal pressure angle phi n and cos lambda. The sliding velocity Vs is given by pi Nw. Nw is the RPM of the worm and dw is the pitch diameter of the worm, divided by 60, because Nw is in RPM. So, divided by 60 it makes RPS, and dw is in mm. So, it is divided by 1000 to make the Vs in meter per second. The torque at the worm gear is Tg is the transmitted load multiplied by half of the pitch diameter divided by 1000, because dg is taken in mm, and so the torque which is acting on the gear will be in terms of Newton meter, where dg is the mean or pitch diameter of the gear in mm. The other parameters of equation 4.1 can be obtained from these datas, which are given in the literatures or the data book. The CS material factor is given by 270 plus 6.328 10 to the power minus 4 and capital C3, where capital C is the center distance between the axis of rotation of the worm and axis of rotation of the gear. So that will be actually C is dg, the pitch circle diameter of the gear, plus pitch circle diameter of the worm divided by 2. But there is a condition for this C that should be satisfied. For sand cast gears, the value of CS is given by this formula based on the pitch circle diameter of the gear. If it is less than or equal to 62.5 mm, then it is constant 13.164. But if it is greater than 62.5 mm and center distance is greater than 75 mm, then it is given by this formula, which is a function of pitch circle diameter of the gear. Now for chilled cast gears, the gears which are made by chilled casting process, the value of CS is given by equation 4.7 based on the center distance and the pitch circle diameter of the gear. For centrifugal cast gears, the CS, the material factor, will be given by equation 4.8 based on the pitch circle diameter of the gear and the center distance. Now chilled casting process, as the material factor depends on how the gear is manufactured or made. So let us see that. The chilled casting process involves pouring molten bronze into a steel or aluminum die base. The die is at a significantly lower temperature than the bronze material, and so the bronze begins cools rapidly or freezes from the outside in. From outside to in, it freezes. The end result of the fast directional cooling process is a bronze gear blank with fine grain structure and outstanding uniformity throughout. So in the chilled casting process, we get the directional cooling, first cooling from outside and it goes inside. So due to this directional cooling, we get fine grain structure, and fine grain structure has a better strength. Centrifugal casting process produces bronze gear blanks as shown here with extremely high purity levels and finer, denser grain structure. By spinning the casting die at high speeds, which produce pressure up to 60 times the force of gravity, all imperfections and impurities are forced into a center riser area. When cooled, the center riser material is machined out and the resulting part is free of shrinkage cavities, gas pockets and blowholes. And so a very good casting is obtained. Now the other factor in the AGMA equation for worm gear is Cm, the material factor we studied. So Cm is the ratio correction factor, and the ratio correction factor Cm is given by equation 4.9, and it depends on what is the gear ratio mg. The gear ratio mg is number of teeth on the gear divided by number of teeth on the pinion. Okay, so in this case your pinion is the worm. So based on the gear ratio you have different equations, and that is applied to get the value of this Cm. Then the next one is the velocity factor Cv, and it depends on the sliding velocity Vs. So if the sliding velocity is less than 3.56 meter per second, then the first formula. If it is more, then this one. So the basic thing is, with the increase in pitch line velocity, the frictional force is increasing and the dynamic effect is increasing, and so you will have a different values of the CV. Then the coefficient of friction is determined from the sliding velocity Vs. If the sliding velocity is 0, that means the stationary condition, then the coefficient of friction is taken as 0.15. The sliding velocity between 0 to 0.05 meter per second, the second formula, with the Vs greater than 0.05 meter per second, the third formula is used. Now we examine some worm gear mesh geometry. The addendum A or HA and the dedendum HF, B or HF is given as HA is axial pitch divided by pi, and this comes as this formula 0.3183 px, and the HF, the dedendum part, is simply for a gear. We have stated, yes, this is the pitch circle, this is the addendum circle, and is the root circle. So this height is called the addendum HA, this is HF. The full depth, summation of these two is the full depth HT. It is given by this one based on the Px. If Px is greater than or equal to 4, then this one. If Px is less than 4, then this formula. The worm outside diameter. The worm, the pitch cylinder of the worm is like this, and the thread is moving in this way. Okay, and when you will see the thread from this section, okay, normal section, it will look like a thread like this. So it will have an outside diameter like this. This is the outside diameter of the worm and the pitch diameter, and then there will be the inside diameter or the root diameter. Okay. So the worm outside diameter DO is dW, pitch circle diameter of the worm, plus 2 times the addendum. It is very much clear here. You have outside diameter like this, pitch circle diameter is this one, this is pitch circle diameter, and above the height, the height of the gear tooth is called the addendum. So this small length is HA, and this small length is also HA. So D plus or DW, which is the pitch circle diameter of the worm, this way, this is DW. So DW plus 2HA will be the DO, outside diameter of the worm. This is the outside diameter of the worm, DO. The worm root diameter, root will be below the pitch, and the depth of the tooth from pitch circle to the root circle is the dedendum. So the worm root diameter DWR is DW and minus of the 2HF. The worm gear throat diameter is given by DGT, the gear. Here we have obtained the dimensions for the worm. Now for the gear, the throat diameter DGT is DG, pitch circle diameter of the gear, plus 2HA, and the worm gear root diameter DGR is DG minus 2 of the HF. The clearance is HF minus HA, dedendum of the your gear and addendum of the mating gear. This is the clearance. The worm face width. maximum worm face width is this one, this length, the length of the worm. Okay, the maximum face width is given by 2 under root d pitch circle diameter of the gear divided by 2. The that will be actually the throat diameter of the gear square minus pitch circle diameter of the gear minus HA whole square. The worm gear face width FG, for the case of worm gear, the face width. That means you have a worm like this, and the worm gear enveloped like this, and this one. Okay, at this side also it will be like this. This is the worm gear. So the worm gear face width, this one, FG, is given by 2 dW. dW is the pitch circle diameter of the worm divided by 3 if axial pitch is greater than 4 mm. We have already studied that in the worm and worm gear, the axial pitch is the parameter which specifies that gear. So if px is less than or equal to 4 mm, then it is 1.25 under root dWo plus outside diameter of the worm plus 2c. C is the center distance whole square minus dWo outside diameter of the worm minus 4 HA. HA is the addendum square. Now the heat loss rate Q DOS from the worm gear case in watt is given by, if the efficiency is E, we have already obtained the efficiency term. So if efficiency of the worm and worm gear drive is E and the heat input is H in, then Q dot will be 1001 minus E H in. The overall heat transfer coefficient U for combined convective and radiative heat transfer from the worm gear case is given by this formula for the case when no fan on the worm shaft. So this is the worm and here is the gear. This assembly will be inside a box, that is called the gearbox. Okay, this is the axis of rotation of the worm and the power will be given from this way, from the outside. So this is the casing and here heat is generated. So this heat will transfer to the outside environment through your convective heat transfer and the radiative heat transfer. From here the radiative heat transfer. Inside there will be some lubricant which will take away the heat. So the overall heat transfer coefficient considering convection and radiation heat transfer is given by this one. Now for the convective heat transfer we must know what type of convection is there, either it is forced convection or the natural convection. So if along the shaft a fan is there and this fan is cooling, then there will be forced convection. So fan on the worm shaft, then this formula will be used, and when there is no fan on the worm shaft, that means the natural convection is there, natural convection, then this formula, this is for the forced convection. The temperature of the oil sump Ts is given by Ts is equal to Ta plus Q dot, the rate of heat generation, and overall heat transfer coefficient, and the A is the lateral area through which the heat will be transferred. this is the casing. So the area through which the heat is transferring, UA. So in place of Q dot, 100 1 minus E H dot or H in is given divided by UA plus TA. TA is the atmospheric temperature. The minimum lateral area A minimum in meter square as per AGMA is given by A minimum is equal to 1.139 into 10 to the power minus 4 multiplied by center distance C to the power 1.7. Now, worm gears bending stress analysis, an alternative way. Previous was the AGMA based bending stress analysis. Now, Buckingham adopted the Lewis equation for bending, and that is given by this. The bending stress which will develop sigma B is equal to WGT, the transmitted load on the gear, divided by Pn, where Pn is the normal module and or the normal pitch, and the normal pitch is equal to axial pitch Px and cos of the lambda. Then Feg is the effective phase width of the gear, and Y is the Lewis form factor related to circular pitch. And the value of Y can be obtained from this table knowing the pressure angle phi n, the normal pressure angle, and the maximum lead angle. The modified Lewis form factor is capital Y. We have to use this one in this formula. So, for 14.5 phi n it is 0.100, for 20 degree and 25 degree lead angle which is this one. So, depending on the value of normal pressure angle and lead angle, we can get the value of Lewis form factor that can be substituted here to get the value of bending stress. Now, designing a worm gear mesh. A usable decision set for a worm gear mesh includes the function for which it is to be used, the power which you want to transmit, the speed and the velocity ratio. Then the design factor or the factor of safety, then the tooth system, what are the different values of addendum, dedendum, pressure angle or the lead angle and others. Then the materials and processes, the material by which the gear is made, the material by which the worm is made and the process by which the gear is, because process affects different factors as we have seen, if it is as cast or it is chilled casting or centrifugal casting. So, the process should also be known to us. Then number of threads on the worm, whether you want to have a good mechanical advantage, then you will go for the single start thread. If you want a good efficiency, then you will go for the multi start thread. So, this ZW should be a priori decision. Now, based on this a priori decisions, we will have a design decisions. That means what should be the axial pitch on the worm, pitch diameter of the worm dW, face width of the gear Fg and the lateral area of the case A, because this will affect the amount of heat that will be transferred, and because the heat is generated inside the casing and that heat should be taken away. So, the lateral area from where the heat is to be dissipated must be known, and that is a design decision. Now, use of equation 4.1 together with the factors CS, CM and CV with an alloy steel case hardened worm together with customary non-ferrous worm wheel materials will result in lives in excess of 25,000 hours. The worm gear materials in the experience base are principally bronzes for the worm gear, and the bronzes are tin and nickel bronzes. Chilled casting produces hardest surfaces, lead bronze high speed applications, aluminum and silicon bronze for heavy load slow speed applications. The material factor CS for bronze in the spectrum sand cast, chilled cast and centrifugally cast increases in the same order. Now, worm gear design is constrained by available tooling, space restrictions, shaft center to center distances, gear ratios needed and the designer's experience. ANSI and AGMA 6022 C93 design manual for cylindrical worm gearings offers the following guidance. Normal pressure angles are chosen from 14.5 degree, 17.5 degree, 20 degree, 22.5 degree, 25 degree, 27.5 degree and 30 degree. And we have seen how with increase in these values the parameters changes. The recommended minimum number of gear teeth is given in table 4.2. The normal range of number of threads on the worm is 1 through 10. Mean worm pitch diameter is usually chosen in the range given by this formula. That means the pitch diameter of the worm should satisfy this condition. That means it should be greater than or equal to C to the power center distance to the power 0.875 divided by 2.002 and it should be less than or equal to C to the power 0.875 divided by 1.068 and the mid range is given by this one, that is to be taken C to the power 0.875 divided by 1.393. So, what we have to do is this dW depends on the C and C depends on the dW. This is the dilemma because C is given by your D of the gear plus D of the worm divided by 2. So, center distance depends on the dW and dW depends on the C. So, what should do? What we do is first of all a initial value of C is taken and from that C we get the value of dW and knowing the dW and knowing the value of dG we get a new value of C. Now this new value of C is substituted here and we get a range and we get a mid range. So that will again give you the next value of dW and this iteration is continued till the other factors are satisfied. Axial pitches for the worm are usually integers and quotients of integers are common. Typical pitches are 6, 7.5, 9, 12, 18, 24, 30, 36, 42 and 48 but others are possible. Table 4.1 shows dimensions common to both worm gear and cylindrical worm for proportions often used. Teeth frequently are stubbed when lead angle are 30 degree or larger. Now the design methodology, how to start the designing of worm and worm gear. A design decision is the axial pitch of the worm because we studied that in the case of worm and worm gear drive, the main specification point is the axial pitch. So a design decision is taken for the axial pitch since acceptable proportions are employed in terms of the center to center distance which is not yet known. One chooses a trial axial pitch. Okay. So having ZW means number of thread on the worm, number of a start and a trial worm diameter DW, we get ZG is from this formula, the transverse module by this and then dW lower range of dW will be this and higher range of dW is this from this formula. This is the lower value of dW, this is the higher value of dW. So we get the higher and lower value and we can select a value of dW in between this lower value and the higher value. Now recompute the center to center distance as C1 is equal to dW1 plus dG divided by 2 there is even an opportunity to make C1 a round number. Choose C2 and set the values. So thereafter, you have to come forward for that. Now, worm gear analysis. Compared to other gearing systems, worm gear meshes have a much lower mechanical efficiency. Cooling for the benefit of the lubricant becomes a design constraint, sometimes resulting in what appears to be an oversized gear case in light of its contents. If the heat can be dissipated by natural cooling or simply with a fan on the worm shaft, simplicity persists. Water coils within the gear case or lubricant out pumping to an external cooler is the next level of complexity. For this reason, gear case area is a design decision. To reduce cooling load, use multiple thread worms because for that efficiency will be more and lesser amount of heat will be dissipated. Also keep the worm pitch diameter as small as possible. Multiple start thread worms can remove the self-locking feature of many worm gear drives. When the worm drives the gear set, the mechanical efficiency EW is given by this formula. This we have already obtained. Then with the gear driving the gear set, that means the gear driving the gear set, the mechanical efficiency EG is given by this formula. To ensure that the worm gear will drive the worm, that means the driving is through worm gear, we have the coefficient of friction under static conditions should be less than cos phi n and tan lambda. It is important to have a way to relate the tangential component of gear force WGT to the tangential component of the worm WWT, which includes the role of friction and the angularities of the frictional force and the lead. Now refer to equation 13.45 solved for WWT. WWT is given by this one. The mechanical efficiency of most gearing is very high, which allows power in and power out to be used almost interchangeably. Worm gear sets have such poor efficiencies that we work with and speak of output power. The magnitude of the gear transmitted force WGT can be related to the output power HO, the efficiency E and the design factor ND by this formula. Instead of taking the power which is given to the driving gear, whether the worm or the gear, we get the output power. What output we are getting due to the efficiency or the loss of the power. So WGT, which is the driven gear, this is given by 1000 factor of safety HO, the output power, divided by pitch line velocity of the gear multiplied by efficiency. Using equation 4.31, we get the heat generated at the worm, heat generated at the gear and the frictional force, then the pitch line velocity and the friction power HF. The friction power HF is WF, the frictional force, then the pitch line velocity divided by 1000 kilowatt. So it is tangential force or the transmitted force on the gear allowed, and it is given by kW dg FEG in Newton, where kW is worm gear load factor in megapascal, dg is the pitch circle diameter of the gear, and Fe is the effective face width of the gear. Kw is determined from a table given here, and for a particular set of material of the worm and the material of the gear, we get as per the thread angle phi n or the normal pressure angle phi n, we get the value of Kw. For example, if we have hardened steel worm and chilled bronze gear and the normal pressure angle phi n is 20 degree, then the Kw will be 0.861 megapascal. And this Wgt is compared with the magnitude of the gear transmitted force Wgt, which is obtained by the output power HO. Output power HO means in the case of worm, due to very high sliding velocity and loss of power due to friction, the transmitted force at the gear is given by 1000 multiplied by factor of safety multiplied by output power divided by pitch line velocity of the gear multiplied by the E. E is the efficiency. And if worm is the driving member, then it will be EW. Sometimes we multiply it to the application factor Ka also. So, the amount of transmitted force you want in your worm and worm gear set is Wgt, but allowed by Buckingham wear load is Wgt allowed. So, the thing is your Wgt transmitted load on the gear should be less than or equal to the Wgt allowed. Okay, this is the example, simple example. In this module, we of the worm and worm gear and design of worm and worm gear, we studied about a gear drive known as worm and worm gear, which transmits power from a shaft which is non-parallel and non-intersecting. We studied different terminologies and the forces which acts on it, and we also found the heat which is generated, and with the thermal analysis we found what should be the minimum lateral area for dissipation of the heat. Thank you.